Hello, and welcome to Lesson 3 of this Introduction to Probability of Wolfram. This lesson is about sample spaces and events. Let's begin. We've talked a lot about experiments and outcomes so far, but that terminology is a bit confusing. We're not really talking about scientific experiments with chemicals being mixed and whatnot, but more of a fundamental mathematical concept. In this lesson, we'll formalize notions concerning outcomes and experiments. Such mathematical concepts require proper tools to manipulate, and for probability theory, those necessary tools are found in set theory. In this lesson, we'll cover sample spaces, events, and set operations. Consider an experiment that occurs with a given set of all possible outcomes. This set is known as the sample space. Note the sample space is all-inclusive. The outcome relevant to the experiment must necessarily be in the sample space. In practice, it can be very difficult to outline all possible outcomes for a given situation, so a catch-all outcome is often used when none of the predicted outcomes occur. For example, if you explore space, you might travel around Earth, the Moon, Mars, or anywhere else. This anywhere else is a catch-all outcome. There's also a special case of sample spaces, binary sample spaces. These only have two outcomes. Either you're close to Earth or you're not, either A or not A. Now, an event is a subset of the sample space. If you pick a cotton ball in this bag, one event could be that you pick a pink cotton ball. Another event could be that you pick a pink or blue cotton ball. An elementary event is an event containing a single possible outcome from the sample space. Here, picking this particular cotton ball is an elementary event. Since there are no orange cotton balls, intuitively here, the event picking an orange cotton ball is not part of the set of possible outcomes, as it is not possible. The possibility is what we aim to define in probability theory. But at the very least, at this point, it should be intuitive to you that this measure of possibility can be ordered, as clearly some events are more possible than others. Now let's take a few more applied examples. Consider ranking 3 horses in a race. We'll be very original and name them A, B, and C. Then with the permutation function, we can get all the orders. So A, B, C, A, C, B, B, A, C, and so on, 6 orderings in total. Now, what about the sum of 2 dice? Well, just table the sum of each die on their values from 1 to 6. And since the minimum is going to be 1 and the maximum 6 for each die, then we get an array from 2 to 12, since there's 2 dice. On that sample space, what is the event that the sum of 2 dice is even? Well, we just need to select the even numbers, and we'll get 2, 4, 6, 8, 10, 12. What about the lifetime of a light bulb? Well, a light bulb can burn instantly or can last a very long time. So intuitively, it should be between 0 and infinity. Now that we have more formal definitions of our sets, it's time to define some useful operations on them. It may be review for some and crucial to others, so you can skip if you know your set theory and you know how to use it in Mathematica. But otherwise, please stick around. The union of two sets A and B is the combination of the members of each set. Note, this union symbol is a special character. Refer to this guide to learn how to write any special character in the Wolfram language. It's really going to be useful because there's a lot of special characters in this course, so you want to get used to it. For union, you'll sometimes see it written like this, which means the union of the sets A1, A2, A3, up to AN. Use this union symbol to get a sorted list of all distinct elements. Now consider two sets, 1, 2, 3, and 3, 4, 5. Now, 1, 2 are just in A, 4, 5 are just in B, and 3 is in both A and B. And for example, 6, and 7 are in neither A or B. So all the elements that are in A or B are 1, 2, 3, 4, 5, which is A union B. The intersection of two sets, A and B, is the set of elements common to A and B. Intersection has a higher priority of operation than union. For intersection, you'll sometimes see it written in this form, which means the intersection of sets A1, A2, A3 up to AN. So in the sets 1, 2, 3, and 3, 4, 5, only 3 is common to both sets, and so the intersection is 3. The complement of a set F is the set of elements in the sample space that is not in F. The complement has an even higher priority of operation than intersection or union. If you take the union of a set and its complement, that is, everything that is and isn't in the event, you'll get the sample space. The notations Fc and F- are also commonly used for complement, but in this course, we'll use F prime. Here, the sample space is from 1 to 7, and the set is 1, 2, 3. So the complement of A is going to be 4, 5, 6, and 7. Now let's go through some important laws of set theory. Union and intersection are commutative, meaning A union B is equal to B union A, and the same applies for intersection. They're also associative, meaning the list of unions can be calculated in any order, and the same applies for intersection. Finally, union and intersection are distributive, so they allow factorization. If you take the union of A and B, then its intersection with C, it's the same as the union of two sets, one, the intersection of A and C, and two, the intersection of B and C, and vice versa. We then have size laws. The size of a finite set A is defined as the number of outcomes in the set. In the Wolfram language, you can use the function length to get the size. But what is the size of the union of A and B? Intuitively, it should be the size of A plus the size of B. But there's some elements here that can be counted twice, namely the elements in the intersection. So you need to subtract the size of the intersection to get the right size number. So we get this formula. Set difference refers to a set A whose elements are not in the set B. Here you select the elements in A that are not in B. If we take the intersection of B complement and A, we get the same zone. De Morgan's laws are like the special distributivity laws of the complement operation. They state that when there's a complement over an intersection or union, the complement can be distributed over each set, and the union becomes an intersection, or the intersection becomes a union. There's also a general form seen here for any number of sets. Let's just prove the first part, since the rest is symmetric. Let's get the union of A and B. Okay, then take the complement. Great. Now remember this shape. Now let's move on to the other part. The complement of A and the complement of B. And then take the intersection. Great. Do you see it? We get the same zone. So that means it's equivalent. So in short, sample space is a complete set of all possible outcomes, and an event is the subset of the sample space. You learned about union, intersection, and complement. Union and intersection are commutative, associative, distributive, and there's also size laws and De Morgan's laws that act upon them. Finally, the prior knowledge needed is now done. Your knowledge of set theory and combinatorial analysis are sufficient to be able to define probability axiomatically, that is, to be done in the next lesson, and all lessons afterwards will talk about probabilities.